All right, hi guys. I recently been working on a larger project which has actually required me to re-implement something I did in college for a homework assignment. Anyway, I always thought the solution was pretty interesting, so I thought it'd be worthwhile to make a little video about it and explain the algorithm that I was taught when I was in college. The algorithm has one major pitfall, which I actually don't really know how to get around, so maybe if you do, you could tell me in the comments. But regardless, I think it's pretty clever anyway, so I hope you enjoy. Okay, let's get into it here. So the assignment goes as follows. The first concept is that you may remember from algebra, sometimes we're given an expression with normal numbers where there are unknowns or variables. We could think of this expression right here, 2 times the quantity x plus 5 minus x minus 10. And then using a few simple tricks from school, for example, we could use the distributive property and turn this into 2x plus 10 minus x minus 10. And then we can combine like terms to get 2x minus x, which reduces to x, and then 10 minus 10, which just cancels out to 0. And at the end, we've taken our convoluted expression here and turned it down into a single term expression, which is much better understood. So the assignment deals with the exact same concept, except instead of normal math expressions with real numbers, instead we're going to be dealing with Boolean expressions, which instead deal with just two values, true and false. So for example, here is an expression. We have in parentheses b and not a, and then that whole quantity ORed with a. And can we simplify this expression? And the answer is yes. There are rules similar to regular algebra rules you may know that apply to Boolean expressions. For example, this OR a can be distributed through the parentheses. So we would get b or a and not a or a. And if we have something ORed with its opposite, so not a or a, that is a tautology. That's always true. So this reduces to b or a. So we can see that just like in normal algebraic expressions, our Boolean expressions have the potential to be reduced as well, even when there are unknowns. So what's the assignment? The assignment is, can we implement a foolproof sequence of steps a computer could use to complete Boolean reductions like the one above? And the answer is yes. The assignment provides an algorithm that you are to implement. When I was in college, I did it in Racket. For this video, I re-implemented it in C++. It uses functional programming, and that's what we're going to dive into for the rest of the video. Okay, so before we dive into the solution itself, we're going to need to think about how we're actually going to represent each Boolean expression and what sorts of expressions are valid for our algorithm. So to do that, we're going to use what's known as an abstract syntax tree. So instead of thinking of our expressions as a sequence of operators and variables and values, we're instead going to think of them as a tree-like structure where each node represents a type of expression. So in our case, we're going to have 6 different types. The first is the variable type. This is the situation where we have a variable named x. The next is an immediate type, which is either true or false. In this case, we're going to use the values 0 or 1, 0 being false, 1 being true. Then we have the composite expression types, which are mapped to operators from above. So, for example, we have not. So if the given sub-expression is false, the not expression is going to be true, and vice versa. We have the OR expression type, which takes two sub-expressions and is only true when one or both of the sub-expressions are true. Then we have AND, which will only resolve to true when both sub-expressions are true. And then finally, the most interesting of them all, and also the most important for this algorithm, and you'll see why soon, is this type, which is known as the ternary. This takes three sub-expressions, E1, E2, and E3. Side by side, or left to right, they're known as the condition, E1, the consequence, E2, and then the alternative, E3. And basically this works like a switch. So if the condition E1 resolves to true, then the consequence is going to be returned E2. Otherwise, the alternative is going to be returned E3. Lastly, for the rest of this video, we're going to be working through an example. It'll actually be the example we did earlier, this expression, and we're going to do each transformation on said expression just to get a feel for how the algorithm works. So this is that expression in our new AST form, and here's a little picture. Okay, so now we can move on to our first transformation, which is known as toIf. Basically, this takes our expression and translates it into an equivalent tree, which contains just variables, immediates, and ternaries. This maneuver really sits on top of three properties, which basically state that not, or, and and all themselves can be written as ternaries. So for example, if we have the negation of an expression E, we can throw E in the condition of a ternary and return false as its consequence and 1 or true as its alternative. So we just switch its value. Or and are a little bit more clever. Conceptually, when we evaluate or, if the first sub-expression is true, we can stop because we know the entire sub-expression is going to be true. So this is seen in the ternary pretty easily. We throw E1 in the condition, and if E1 is true, we're just going to return true from the consequence right away. Otherwise, the alternative is going to be evaluated as a backup plan, and that'll be E2. Similarly, when we're evaluating an AND statement, if the first sub-expression is false, we can stop right there. We can just return false right away. So we can throw E1 in the condition again, and if E1 is false, we return the alternative right away of false. Otherwise, we do E2 kind of again as like a backup plan. The actual transformation, the actual code, is going to look very similar to these three properties, except it's going to be recursive. And to describe the method, I'm going to be using the pseudo functional syntax. So basically, all of these cases are basically identical to the cases listed up here, except they are recursive, right? So, for example, if we're trying to do toIf of a not expression, we just return the ternary as organized above, except now we're going to take our sub-expression and we are going to turn it into an if expression first. That way we can guarantee that the if expression we can guarantee that the expression we return only contains ternaries, variables, and immediates, something we talked about earlier, right? The only thing that isn't really listed above in the properties is this, which is that if we get a ternary, we basically just leave it as is, although we, again, recursively call on all three of the sub-expressions. Anyway, we can see this in action on our example. Remember, this is our initial expression, and we are going to be kind of evaluating kind of like a bottom up, or at least that's how I'm going to show it in these steps. So for example, if we start with the topmost OR, it's going to try to convert its first sub-expression, the AND, to an if statement, or an if expression. Then that's going to try to convert B, which is going to remain as is, and then it's going to try to convert the not sub-expression. That the not is going to be the first sub-expression we get a hold of that we can change. So that would look something like this. So now we no longer have the not. Instead, we have a ternary using A as the condition. Then we can kind of bubble up. We go to the AND above that, and now the not expression we just translated now is itself the consequence of our new ternary, where B is the condition. Finally, we have to deal with the OR statement, the topmost OR expression, I should really say, and that itself turns into a ternary, where the big ternary we just computed, that is now in the condition position, and then the 1 will be the consequence, and A will be the alternative. So you might want to kind of scroll back through this video and convince yourself, how this works. But yeah, that's the basics for toIf. Okay. Now for the next transformation, which is known as norm. Before I define how the transformation works, I need to define what a normal if expression is. So in the last step, we took our normal expression, turned it into an if expression, which contains just variables, immediates, and ternaries. A normal if expression is the same thing, except the condition of every ternary in the expression must only be an immediate or a variable. So let's see what I mean by that. This is an example of a normal if expression. It's an if expression, and the condition is an immediate. Variables and immediates themselves are also normal if expressions. However, this situation is not normal, because in the condition, there's a ternary, right? The consequence could be a ternary, the alternative can be a ternary, but the condition must be a variable or an immediate, right? This is probably the most important part of the algorithm, and we're going to see why in the next step. But in this step, we need to create a function which takes an if expression and makes it normal. So to implement this behavior, we're going to use a combination of two different functions. The main function, intuitively named norm, will take an if expression and return the normal version. This function almost relies entirely on kind of a secret helper function named join. Join is a little bit different. The way join works is that it is given an if expression whose 3 sub-expressions are guaranteed to themselves be normal. And what join must do is return an equivalent expression which itself is normal, right? So what I mean by that, for example, is, this would be a valid call to join. We are given an if expression, and we are told that the condition, the consequence, and alternative are all normal. So E4 and E5 are normal, and then this given if expression is also guaranteed to be normal. However, the entire if expression is not normal because this, the condition is itself a ternary. So we need to do a little bit of work to convert this into a normal if expression. So the method's actually pretty simple. What we do is we kind of take the innermost condition and we kind of boost it up to the outermost if expression. So now this Vx, or the variable x, now becomes the outermost condition. And then what we do is we use E2 as the condition for a new if expression, which switches between E4 and E5. And then we do the same thing with E3. So now E2 and E3 themselves become conditions. You might want to think about why conceptually this makes sense. However, to note on the recursive element of this function, we know that E2, E4, and E5 are all normal. We also know E3, E4, and E5 are all normal, right? So we know that this if expression, while itself might not be normal, is valid to pass into join. So we actually call join on these new ternaries we're creating. And the result is kind of this recursive behavior, which later we'll see actually can be kind of problematic. But for now is sufficient to turn just any if expression into a normal if expression. The example might not be as easy to follow as with the toIf, but I wanted to make it conceptually as understandable as possible. So this is the original if expression we're given. And we see in the condition, we have this big if expression. Now, it so happens, the nice part about this example is that this if expression right here is already normal. So it has a condition which is a variable b, and then its sub-expressions are also normal, right? This ternary has a condition which is a variable, that's fine, and then the alternative is 0, that's fine, right? But again, the if expression as a whole is not normal, right? So what really goes on here is that we kind of need to think of all the paths we can take in this condition if expression. If b is true, we're going to go down a level. And then if a is true, we're going to hit 0. If b is true again, we're going to go down a level. If a is false, we're going to hit 1. If b is false, we're going to hit 0. And we realize that there really are only 3 results we can yield from this condition if expression. We can get down to this 0, down to this 1, and across to this 0, right? Depending on the values of b and a, right? So what normalize is going to do is it's going to take this entire if expression in the condition position of the outer if, and it's going to raise it up to become the new outer if. And then all of these results, which I outlined in green, are going to become conditions of new ternaries. And everywhere there's a new ternary, the consequence and alternative are going to be these purple nodes I highlighted, right? So let me show you what that looks like. Again, this is probably the hardest to understand part of the algorithm, but it looks something like this, right? So now every time we saw a result highlighted in green, it is now a condition of a new if expression, right? So the 0 from going from b to a, that is a condition which has consequence and alternative 1 and a. And the same goes for the other 2 paths we could take. And the result is, completely normal, right? Again, we're going to see that this step can be problematic later with the size of the tree. However, conceptually, it is, it's rigorous. It works. Anyway, so this is the most expanded the tree will be. And now we can kind of start reducing and evaluating the tree. So we're in the home stretch here. So the next transformation I called eval. As a disclaimer, that might not be the best name. I think usually when people think evaluate, they mean take an expression and turn it into one value. That's not really what this necessarily does. It's going to evaluate the expression as much as it can, right? Reduce it as much as it can. But we can see the intuition here. So the first few cases are pretty simple and nothing really surprising. If we evaluate a variable, there's nothing really we can do. If we evaluate an immediate true or false, not much we can do. If we get to a ternary and its condition is true, we can return the evaluated consequence. And same with the situation where the condition is false, but instead we're going to return the evaluated alternative. The special case, and in my opinion, the most interesting part of this algorithm, and also the motivation behind making our expression normal, is this situation where we are given a normal if expression. In this case, we do not know the value of the condition. However, we do know, because it's normal, it's just going to be one variable. Now, conceptually, if this expression were to resolve to the consequence, the variable x would have to be true. Similarly, if it were to reduce to the alternative E3, the condition would have to be false. So in a way, we know all instances of x in E2 really are going to resolve to true if they're ever evaluated. And all instances of x in E3 are going to resolve to 0 if they're ever evaluated. So what we can do is we can kind of take advantage of that fact. So before, this is kind of like pseudo syntax here, but what we're going to do is we're going to evaluate the consequence and alternative given this, this cool, clever trick. Basically, what this means here is we're going to take E2 and we're going to find all instances of x and we're going to replace it with true. And with E3, replace all instances of x with false. Of course, if you were to code this yourself, I wouldn't recommend actually rebuilding the tree. Instead, I'd recommend using some sort of environment. I used some sort of map when I did this in C++. There's no need to actually replace the nodes. Anyway, after that step, you're kind of in the clear. Basically, you can check if the consequence and alternative end up being the same. You can return either one of them. You no longer need this, overarching ternary if the two possible results are the same. This one's kind of cool. If the consequence is true and the alternative is false, that is really just equivalent to just the variable in the condition itself. We don't need this ternary involved. It's a little bit redundant. And then finally, maybe we did our evaluation on the consequence and alternative, and maybe things were simplified, but we can't really make any moves at this level. Then we just return, what you'd expect, just the ternary as it is, but with the consequence and alternative reduced. Okay, so now we can move to the example, which we are going to walk through just like we did with toIf. So we're going to start with the normal if expression we've been given, and we're just going to start evaluating it kind of top down here. So we're starting with b as the condition. Let's first substitute b with true everywhere it occurs in the consequence, which is going to be this big ternary. It so happens there are no occurrences of b, so no substitution is needed. And then what we can do is we can evaluate the consequence now. So now we're going to evaluate this big ternary. So we're going to do the same thing, but now move down to this condition of a, and we are going to replace all instances of a in its consequence with 1. So just like that, that's what this red square signifies. Now we're going to evaluate the consequence. We see that our condition is an immediate, it's 0. So we're going to select the alternative of this ternary, which is 1. So that kind of gets bubbled up. So now we have, we've successfully evaluated the consequence of this lower ternary. And now we're going to evaluate its alternative. Before we do that, we're going to substitute all occurrences of A with 0 in the alternative, which looks like that. Blue is signifying kind of our previous steps here. Now we can evaluate the alternative. It so happens our condition is already an immediate, so we can, because it's true, we can select the consequence, which bubbles that up as 1. Now we've successfully evaluated the consequence and alternative of this ternary. Now we can kind of compare the values. They're equal, so we can bubble up. We could just pick one and bubble it up. So that's what that looks like. We can kind of erase the A condition that's no longer needed. And this is what we're left with so far. Now finally, we're back at our topmost if expression, and we need to evaluate the alternative now. Again, first thing we're going to do, we're going to substitute all occurrences of B with false in the alternative. There are no occurrences of B in the alternative, so we can simply evaluate right off the bat. Lucky for us, the condition of this ternary is already an immediate, so we can just select the alternative right off the bat because the condition is 0. So we're going to bubble up this A. And that's what we're left with. So we went from this massive tree up here that objectively is confusing, and we got it down to something simpler than what we started with in the very, very beginning of this video. Anyway, for the sake of time, I'm going to go through the last transformation very fast. It's basically the inverse of, it really is the inverse of toIf. So basically, now we're taking an if expression, and if we can, we're going to convert it back to our, regular, more common Boolean operators like not, or, and, right? So again, this is just the reverse of the rules we saw before. Like if we have an expression in the condition and its consequence is 0, alternative is 1, we know that's a not, right? And same goes for these cases with or and. So what that looks like in the example, we have our tree from earlier. This looks a lot like an or statement to me, so we reduce it and we change our ternary to an or, and we can drop this unnecessary 1. And there we go. That's the end of the algorithm. So I hope you enjoyed. And now we're going to look at some C++ code and also the potential pitfalls of this algorithm. All right, so I don't plan on going too deep into the C++ because I think that wouldn't really be worthwhile. But I just wanted to talk about like the general design. Basically, I had this abstract parent class called an expr and expression, and then it has a concrete derived class for every node type we talked about when we defined the the AST. So there's a node there, there's an expression type, or there's a derived class, and there's a derived class ternary, right? And they all are designed exactly how you'd expect. Instead of adding the behavior for each transformation to each individual class, instead I allowed the ability for the user to define custom visitors. If you don't know what a visitor is, it's this thing I learned about in college. It's pretty interesting. The idea is if you have an abstract class which has all sorts of derived classes, you may want to add a behavior to the abstract class that is implemented by all the derived classes. And to do that, you'd have to go into every single class, every single derived class, and write in the code, which is first of all, could get extremely bloated and unorganized. And also, you might not even have access to these derived classes. That might not be something you're allowed to modify in the first place. So instead, sometimes when making this type of class structure, another class will be given known as a visitor. And what this will do is it'll have abstract methods which correspond to each of the derived classes. And then if you have an instance of an expression, for an example, you don't know what type of expression it is, and then you have an instance of a visitor, you can just pass the visitor into the expression, and under the hood, it will call the correct behavior based on what type of expression you're actually working with. This is all without you even knowing what expression you're working with, right? So it's kind of cool. And, I could go more into that, but maybe that's not really the point of this video. Here's a good example, though. One visitor I define is for the toIf transformation, the very first transformation we went over. So I called that bool toIf transformer. And this is the case where we get an OR expression. I called it an OR app. So we're given a pointer, E, to an OR expression, and now it's our job to make it, or to create a new expression, which is normal. Again, this is functional, so I don't do any mutation to the tree I'm given. So it works just as we talked about when we went over it in the README. So we get our first sub-expression, we transform it into an if expression. We get our second sub-expression, we transform it into an if expression. And then we return a new ternary with the form we discussed, right? With the equivalent form. And that's the same for all the other cases, like and works as you'd expect. What is this? Oh, I had parentheses. That doesn't really do anything. Not app works as you'd expect. One thing that is kind of interesting, like a little quick optimization I did for ternary, which I thought was kind of interesting, was here that for ternary, if you remember, we just get the if expression of the three sub-expressions, and then we create a new ternary with those results. However, there is a chance that that the given if expressions or the given sub-expressions are themselves already if expressions, in which case the ternary we were given here doesn't need to be changed at all. It already is an if expression. So that's kind of what this does right here. What it does is after calculating the new condition, the new consequence, the new alternative, it does a simple pointer comparison to see if they're actually the same trees. And if there are, there's no need to create a new ternary. Rather, we can just return the original, right? Again, this all sits on top of the fact that this whole design is functional. Anyway, with that, we can go into a quick little demo. So I've set up this main function, which is going to run each transformation one after the other. So first, it's going to parse our expression from text, and then it's going to transform it into an if expression, make it proper or normal, as I said earlier. It's going to optimize, or that's the same step as evaluate. And then finally, it's going to reduce and print out the final form. To confirm this works with the example, I have this string. I'm using prefix form, not infix like maybe you'd expect. I just did this because with prefix, you don't really need parentheses. Also, it's a little easier to parse. And I use the question mark for the ternary, and the ternary has not two, but three sub-expressions. So I felt like that fit a little nicer into prefix rather than infix. So in this situation, A is the condition, B is the consequence, and C is the alternative. So anyway, let's run it with our example here. We have or, and then B and not A, and that ORed with A at the end, right? So let's write this, make I'm using CMake. So we can look through all the forms here. And it's looking good. We get the if form, which only contains question marks, like we'd expect. The normal if form, there are never 2 question marks in a row. Maybe you could convince yourself why that's necessary. And we have the evaluated form and the final form. So it looks good. You know, if we wanted to, we could juice this up a little bit, just as a proof of concept. If we wanted or, and or B, C, B, I don't know. Make this not B. Let's see what that does. So now it's a little bit more complex. We run it, and we see that we actually end with a ternary, which isn't always ideal, but it's definitely more simple than the starting expression. Anyway, kind of as the last part of this video, I wanted to talk about the real pitfall of this algorithm, which I don't really know how to get around. And maybe if someone does, they could tell me in the comments, which is that if you form your expression in a way such that there are many nested conditions with ternaries. So, for example, there's a ternary, and its condition is a ternary, and that ternary's condition is a ternary, and so on. The normal if form actually becomes exponentially large. So I could kind of show you what I mean by that. Let's say we had or A and B, or A or B, I should say. Okay, the normal if form, pretty small, just like we'd expect, right? Now let's say we take this, but now we add another layer. So now we're taking these 2 or expressions and we're oring them together. Let's see how big this is. Okay, it's a little bit bigger, but not a big deal. And maybe we could or these guys together now. Now this if expression, while it might be a little hard to parse with in this prefix form, regardless is really not very complex and should be easily reducible. But if we run again, now our normal if form is pretty large. Let's say we go one more level up. It still reduces correctly, but now let's see how large this normal if expression is. Absolutely massive. And I bet if we nested this one more time, my computer would probably run forever. So this is like the massive pitfall. And I've done some thinking about it, and I have some ideas, but maybe I could make another video about it, and maybe somebody could help me out. Regardless, that kind of ends this video. So thanks for watching if you made it this far. The code is part of kind of a private project, which isn't really posted publicly on GitHub. But the README file, the notes file we were looking at earlier, I did make that public in kind of like a miscellaneous YouTube repository on my profile, and I'll post the link in the description. So thanks again for watching.